And hearty good morning, everybody. Welcome back to Abstract Algebra. Plan for today, we're going to prove some theorems relating to showing things are subgroups. I've got my usual office hours this afternoon from 2 to 3, Tuesday tomorrow morning from 10 to 11:30, tomorrow afternoon from 1:30 to 2:30, and Wednesday at the same times as today. If you want to stop by and talk with me at all. Homework 2 will be due on Friday. Homework 1, I haven't even started grading because I've been trying to figure out the grading for my other class. And oh my gosh, I have so much grading this semester. So, I will try and get this class graded as soon as I can, but in general, it will typically be, I'm guessing, about a week before I can get this class graded because this class takes a while to grade, and there are many of you. So, such is the way of things. But I've seen some of your submissions, took a glance through them, they look pretty. What's I gonna say? How can you tell if a mathematician is an extrovert? You tell a mathematician is an extrovert if when you're talking to them, they look at your shoes instead of their own.
Great.
So, last class we talked about lots of examples of these things called subgroups, where in general we say that H is a subgroup of G if H is a subset of G, meaning every element in H is also an element in G, and if H itself forms a group under the same operation as G. And our notation for subgroup is sort of the less than or equal to symbol. We say H less than or equal to G. This symbol really just means H is a subgroup of G, which we'll be using throughout the semester. And on Friday, we looked at a bunch of different examples of subgroups, including the center of a group, the centralizer of an element, the group generated by a single element. And today, we're gonna prove some theorems related to these subgroups. Any questions or comments before we get started for today? All right. So suppose you want to show that H is a subgroup of G, meaning you want to show that H is a group under the same operation as G. Normally, to show something is a group, how many things do you have to check? You have to check 4. So we're going to prove some theorems today that kind of give us some shortcuts to showing H is a subgroup of G. Because if we're already assuming G is a group and H is a subset of G, then we can get a few things for free. So I'm going to be in the same packet as Friday on the page that says at the top theorem, one-step subgroup test. This is going to be a theorem that tells you, in general, you can prove H, given some subset H of G, you can prove H is a subgroup of G by only checking one thing instead of 4. Which is convenient because checking 4 things is glitch. So here's the theorem. It says, let G be a group. And H, we're going to assume, is a non-empty subset of G. Then, if AB inverse is an element of H, whenever A and B themselves are elements of H, then H is a subgroup of G. So according to this theorem, if we have a non-empty subset of G, H needs to be non-empty because technically the empty set, the set with anything in it, can't possibly be a group because groups have to have at least one element, the identity element. So H has to be non-empty. We're assuming H is a subset of G. And then this is saying the only thing we need to check to show that H is a subgroup of G is to check if given any 2 elements of H, first element times the inverse of the second element has to be in our set, has to be in H. So let's see if we can prove this. What should any good proof start with? Uh-oh.
Does it let G be a group?
An introduction, indeed. Let G be a group. We need to introduce the things we're going to be working with. We're going to let G be a group. And we're going to let H be a subset of G. Subset, by the way, is sort of similar symbol to subgroup, except it's sort of this curly C instead of a less than symbol. We're going to let H be a subset of G, such that for any A, B, and H, it's true that AB inverse is in H. So in other words, we're assuming we have some subset of H, I should say H non-empty. We need H as a non-empty subset of G, and we're assuming that H has this property, that given any two elements in H, the first element times the inverse of the second element is always going to give us something in H. And our goal is going to be to show if we have an H with this property, H has to satisfy the four necessary conditions in order to form a subgroup. So, yes, Nick?
Is AB inverse A times B inverse or AB inverse?
It's A times B inverse. If I ever want to talk about the inverse of the product, I'll write it out like this. Like AB and then parentheses with an inverse. If you ever see me write this, this just means AB inverse is always going to be A star, just the inverse of the group. Or, again, depending on what your group is, this may not be multiplication, this is just whatever the group operation is from G. So we need to show so if we want to prove H is a subgroup of G, we need to show four things. We need to show H has closure, H has associativity, H has an identity element, and H has inverses. Ba-ba-boo, ba-boo, ba-boo. Megan, where would you like to start?
Closure.
I don't want to start there. Megan, you tell me. Sally, where would you like to start?
Inverses.
I don't want to start there. Peter, where do you like to start? Identity, that's a good place. We can start there. It's going to turn out we can't do closure until we prove identity and inverses. And we can't do inverses until we have we show an identity. So I'm not just being mean, but there is a reason why I didn't want to start with those two. So let's see. We're going to start by proving identity. So what would we like to be able to say is the identity element of H? Given that H is Wayne, stop that. Sorry. I'm already distracted. So we're assuming that H is a non-empty subset of some group G. What would we like for the identity element of H to be? Yeah, we'd like to be able to take the identity element from G and show that that also works as an identity element for H, which mainly is going to boil down to being able to show that the identity element from T is in fact an element of H. So here's going to be our proof of identity. We're going to let X be any element in H. We know H is non-empty, so there has to be at least one element in H. What do we know about XX inverse? I claim we can say two different things about XX inverse, given that X is an element of H. Yeah, by definition, this has to be the identity element of G. Here, I'm not just writing E, I'm putting E sub G to make it clear we're talking about the identity element of G. We're not assuming it's an identity element yet for H. So, by definition, if we take X and multiply by X's inverse, we're going to get the identity element of G. I claim we also know something else about XX inverse, given how we defined H. Given sort of this property right here, what can we say has to be true about X inverse?
Every value in H has an inverse.
Well, we don't know. Well, we know it has an inverse in G.
Okay.
But what does this property right here tell us has to be true about XX inverse if we're making an initial assumption that X is an element of H?
Then X inverse is in H as well.
Exactly. Since X is an element of H, and since X is still an element of H, it has to be the case that if we take this thing in H, X, and we do the group operation with the inverse of this thing in H, namely X inverse, according to this property right here, that X times X inverse has to be an element of H. But then, but also we can say X inverse is an element of H, since X is an element of H. And thus, we can say that whatever the identity element of G is, has to be an element in H as well. And satisfies that A times EG is equal to A is equal to EGA for all A an element of H. Hence, the identity element in G also is the identity in H. So in other words, we showed that that using this property right here, we assumed about H. We showed that the identity element in G has to be an element in H automatically, and since it's an element in H, it can also serve as the identity element in H. Because we already know that if you take the identity element in G and multiply it by anything in H, you get back that same thing. That's a property of it being the identity element in G. Any questions or comments about how we proved identity? Okay. Where should we go next? Becca, what would you like to prove next? No, we're still not ready for closure. Dave, what would you like to do next?
Still inverses.
Inverses. Done identity. Now we can do inverses, I think. So now, this is part of the same proof. I'm just kind of separating our work. So now we are going to let A be an element in H, and our goal is going to be to show that A inverse also has to be an element of H. Well, we know that since the identity element, H has an identity element, E, what can we say about A times E inverse? No, that's not the one I wanted. E times A inverse. That's the one I wanted. We're assuming that A is an element in H. We also showed before that H has an identity element, E. So if we take E, which is an element in H, multiply by the inverse of A, which is an element in H, that this has to be in H by this property here. I'm going to call this property star and say that by property star, we know E times A inverse has to be an element of H because it's equal to thing in H times inverse of thing in H, which we assumed is always going to be an element of H again. But what else do we know about E times A inverse? What is that going to be equal to?
A inverse.
Yeah, E is the identity element, so E times A inverse is just going to be A inverse. Then since E times A inverse is equal to A inverse, we know A inverse is in H as well. So in other words, given any element in H to start with, the inverse of that thing has an inverse that also is going to lie in H. So things in H have inverses in H. Okay. All right, Elaine. Now, got two things left we need to prove. Now you can do either one.
Let's do closure.
Let's do closure. Okay. Saving associativity for the bitter end. So next up, now I claim we're ready to show closure. So for closure, what do we need to show? We need to show that if we take two things in H and combine them with the group operation, we need to be able to prove that that gives us something else in H, right? So now I'm going to let A and B be elements of H. Using what we've shown about inverses, I claim that tells us that B inverse is in H, since elements in H all have inverses in H. So using a property that we just proved, that if we start with something B in H, that the inverse of B has to also be in H. And now, check this out. I'm going to take A times B inverse inverse. What is B inverse inverse?
B.
So it's going to be B, but A is an element in H, B inverse is an element in H. We have this nice property that says if you take thing in H times inverse of other thing in H, you always have to end up back in H. It's going to have to be in H by star, since A and B inverse themselves were elements in H. So we actually needed inverses, the property of inverses, before we could prove closure this time. Because in proving closure, we had to rely on the fact that if we started with something in H, its inverse has to be in H. And then we could use this property star that says thing in H times inverse of thing in H, where the thing we're inverting is actually B inverse. That tells property star that we started with tells us that A times B inverse inverse has to be an element in H, but B inverse inverse is just going to be B. I think we proved that. We didn't actually prove that. You all can prove that. And so that tells us that A times the original B also is going to have to be an element in H. Any questions about what we did here? Or what does that leave us?
Associativity.
Associativity. It's the last one. The bane of my existence. It's actually going to be pretty easy in this example. So the last thing we need to prove is associativity. So we're going to let A, B, C all the elements in H. Then, since H is a subset of G, meaning everything in H is an element in G, goodness, all the giggling. I claim that tells us A, B, and C have to all be elements of G, yeah? If they're elements of H and every element of H is an element of G, A, B, and C have to be elements of G. Here's the cool thing. Then since G has associativity, AB times C has to be equal to A times BC. And there we go. We have associativity in H. We showed that given three arbitrary elements in H, AB times C has to be equal to A times BC. That's all we need to show for associativity. H sort of just inherits associativity from G. It's the saying ABC as elements of G have to have this associative property. Therefore, as elements of H, they also have to have this associative property, since everything in H also happens to be in G. Yeah.
So we could have started with associativity if we wanted to.
That was going to be my next question. Is like, what was the order we needed to do this in? Turns out associativity we could have done at any time, but we needed identity to do inverses, and we needed inverses to do closure here. Associativity surprisingly ended up being the easiest of the four, when often it's the most difficult / annoying. But there we have it. I guess let's write a conclusion for our proof. Thus, H is a subgroup of G. We've proven that H has closure. We've proven that it has an identity element, just the identity element of H. We've proven that H has inverses, meaning given any element in H, it has an inverse in H. And we've proven that H has associativity. All of these relying heavily on the fact that, that H is a subset of some group, of something we already know to be a group G, and we're already assuming that G has all of these things. Like we're assuming G has an identity element, that any element in H has an inverse in G, and we're using the associativity of G. We're all kind of necessary parts of this proof. But this goes to show, if you want to prove you have some non-empty subset H, you want to show it's a subgroup, from now on, you don't need to check all four things. You just need to prove this one property.
So property star, we're just assuming that's true because it inherits it from group G.
Well, we're assuming we have to have something that has property star. Basically, our theorem is saying if we have some H that has property star, then it has to be a subgroup. If we have some H that doesn't have property star, we make no claims about whether or not it makes a subgroup of G. In fact, if it doesn't have property star, you can't actually show it can't be a subgroup of G. That would be a different proof. Any other questions or comments about this one? Let's do a quick example where we use this to prove something is a subgroup. So I didn't actually leave you room in the packet to do this, and I apologize for that. Maybe you could, I think the back page of the packet would be a good space for this one. Well, I didn't mind. So let's look at an example where I claim we're going to let H be the set of all matrices, 2 by 2 matrices, of the form 1, 0, n, 1, where n is some integer. And my goal is going to be to show that H is a subgroup of GL2R. In other words, we're just taking the set of all 2 by 2 matrices with 1, 0, 1 in the top left, top right, bottom right positions, and the bottom left it can be any integer. We're assuming this set of matrices is going to be form a subgroup of GL2R. Can someone remind me, GL2R was a group under which operation?
The multiplication.
Exactly. So when we say a subgroup, technically we mean it's a subgroup of GL2R under multiplication. I'm not going to be writing that from now on because it's just assumed when we talk about GL2R as a group, we assume we mean under multiplication. Normally, before this one-step subgroup test, we would have had to test 4 different things. We'd have to show associativity, which we can do, but it's a lot of matrix multiplication that's rather bollocks. We could show an identity element. we need to show inverses, and we need to show closure. If you take two matrices of this form, their product is something of this form. Instead, the one-step subgroup test gives us a shortcut. And that all that we need to do is take we're going to take two arbitrary elements in H and show that the first times the inverse of the second one is in H. And that'll be enough to show H is a subgroup of DL2R. So let's start. I'm going to let A be of the form 1, 0, A1, and B be of the form 1, 0, B1. We're going to assume that these are arbitrary elements of H. So we're taking two arbitrary elements of H. Our goal is going to be to show that A times B inverse has to be in H. I claim that B inverse is equal to 1, 0, negative B1. How can we check that B inverse is equal to that thing relatively quickly? With that, and if you can, please give me an answer that doesn't involve row reducing.
Multiply B and B1 to get the identity.
Yeah, if we can multiply these two things and get the identity, then this would have to be the inverse of B. The inverse is going to be 1, 0, B1, 1, 0, negative B1, which is, let's see, 1 times 0 is 1, or 1 plus 0 is 1, 0 plus 0 is 0, B minus B is 0, 0 plus 1 is 1, equals the identity element, and GL2R. Cool. So we know what B inverse has to be. Given this B, it has to be of the form 1, 0, negative B1. Then A times B inverse is going to be 1, 0, A1 times 1, 0, negative B1. Let's see, 1 plus 0 is 1, 0 plus 0 is 0. A minus B is going to be A minus B. 0 plus 1 is 1. Is this matrix going to be an element in H? We're assuming that big A and big B are elements in H. Meaning little a and little b are going to be integers. Does this have to be an element in H? If not, yeah, it does. Because since if A and B themselves are integers, A minus B also has to be an integer. The difference of two integers is going to be an integer. I'm okay if you assume that, because I'm going to. Thus, we've shown that given any two arbitrary elements in H, the first times the inverse of the second has to also be in H. Thus, by the one-step subgroup test, H is a subgroup of DL2R. Thus, by the one-step subgroup test, H is a subgroup of GL2R. Boom. No need to check H has associativity. No need to check H has the identity element. Oh, that is pretty easy to check. No need to check closure. No need to check inverses. We just had to check this one thing, that that given any A and B in H, A times B inverse is also in H. Questions or comments? Okay, now that we've done it with one step, let's talk about how we can show it in 2 steps. Less efficient. This next step's going to be the two-step subgroup test, which is basically going to say if you have a non-empty subset H and G, the only thing you can show that H is a subgroup of G just by proving closure and inverses. No need to check identity, no need to check associativity. So let's see, let's flip to the right page. So here's our theorem. It's going to be the two-step, one-step, two-step. Sounds like the subgroup test for dances or something. That would be cool. So we're going to let G be a group, and H a non-empty subset of G. If, whenever A and B are elements of H, we have that first of all, AB is in H, and second of all, that A inverse is in H, then H is a subgroup of G. So here's our proof. Stephanie, what should we start our proof with? Let G be a group. And let H be a subset of G as defined above. Here's where I'm going to be lazy, and instead of saying let H be a non-empty subset of G such that whenever A and B are in H, we have that AB is in H and A inverse is in H. I'm just going to say let H be defined as defined above. Meaning we're assuming H has closure, we're assuming H has inverses. So our goal is going to be to show H is a subgroup of G. Check this out. I'm not going to prove I'm not going to go through associativity and identity arguments. Instead, I'm going to let A and B be two elements of H. And then by property 2, B inverse has to be an element of H. Because we're assuming we have H that has inverses, so since B is an element of H, it has to have an inverse in H. And then by property 1, I claim AB inverse has to be an element in H. Since A is in H, since A and B inverse individually are elements in H, by property 1, that tells us AB inverse has to be in H. So I've showed given any two elements in H, A and B in H, AB inverse has to be in H. I claim we can finish this proof in a single sentence.
Using the one step.
Yeah. Thus, by the one-step subgroup test, H is a subgroup of G. We've proven property star, and we've proven that H has property star. And the one-step subgroup test tells us that any H with property star has to be a subgroup. Therefore, by that test, H is a subgroup of G. The one-step subgroup test H is a subgroup of G. Another case of we were able to use a previous. Oh, my voice back. We were able to use a previous theorem, the one-step subgroup test, to make proving the two-step subgroup test much easier. By just showing that if you have H with these properties, it also has to have the property star from the one-step theorem. Questions, comments, concerns? So, in general, if you want to prove, if you have some H that you want to prove is a subgroup of G, you don't need to necessarily, you can choose how you want to prove it. If you really want to, you can go through and check all 4 of the group properties, or you can use the 2-step subgroup test, or you can use the 1-step subgroup test. Whichever one's your favorite, go with that. Translation, whichever one is going to involve the least amount of work for Dr. Verstical to grade, go with that one. That should be your favorite. Okay, now the fun one. The finite subgroup test. Turns out, if you have H is a non-empty subset of a finite group G, meaning a group with only finite meaning elements like the dineutral groups, then you don't even need to check inverses. All you need is closure in order for H to be a subgroup of G. So let's see. This is the finite subgroup test. Here, we're going to let H be a non-empty, finite subset of group G. Then we can say if H has closure, then H is a subgroup of G. It's sort of like the two-step theorem, or the two-step test, but in the two-step test you have to check you have to check for H having both closure and inverses. According to this theorem, if H is finite, closure is the only thing you need to check. And if your group has closure, then if H has closure, then it'll automatically be a subgroup without having to check for inverses, which is pretty nifty. All right, here's our proof. What's the first line of the proof? Don't worry, I'll stop asking this eventually.
Let G be a group.
Let G be a group. And then we're going to let H be a non-empty finite subset of G with closure. Non-empty finite subset with closure. What's the only thing we need to check in order to be able to use another theorem to say H is a subgroup? If we were to use the two-step theorem, we only need to show one thing about elements in H in order to get that H is a subgroup. What can we show that'll get us there?
A B inverses in H.
We can do that if we use the one-step theorem. How can we show one other thing and then use the two-step theorem?
You just need A inverses.
Yeah, we need to show given any A in H, we need to show A inverse in H. If we can show that, then we can then say, thus by the two-step theorem, H is a subgroup. So I'm going to let A be an element in G. Blah, 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 H. And I claim we have two cases. First case, A is the identity element. If A is the identity element, do we know that A has an inverse in H? What's A inverse in that case?
E.
Yeah, A is its own inverse if A is the identity, so that's an easy case. If A is equal to E, then A inverse equals E, is equal to E. So A inverse is in H, because we assumed A was, and it's equal to A inverse. Second case is the fun one. So case 2, A is not the identity element. And what we're going to do is something a little bit unorthodox. We're going to consider the sequence of elements A squared, A cubed, A to the fourth, and so on. Where you may remember from last time, we defined A to the K to just be A star, A star, A, K copies. So in other words, we're considering a sequence of elements A star A, A star, A star A, A star, A star, A star A, and so on. We assumed that H has closure. That's the only thing we assumed at the start. Using the fact that H has closure, what can we say about all these elements? A star, A star, A star, A star, A, etc. Right?
Oh, in H.
Yeah, since A is at H, then if we take A star itself, however many times we want, we're always going to get something that's still in H. Since H has closure, all of these elements lie in H. You could sort of do this inductively if you want. Say, since A is in H, A star A has to be in H. Since A and A star A are in H, A star A is in H. Since A and A star A are in H, A star A is in H, and so on. Is everyone okay if I just leave it like that? Okay. I claim we know something else about this list. Nick?
It ends
It ends. Why is that?
because H is finite.
Indeed. So I wouldn't say necessarily that the list ends, but it has to repeat itself. Yeah. And here, notice that we haven't yet used the fact that we assumed that H is a finite set. But that is something we assumed, and now we are ready to use it. And here, we're going to use it to say, eventually, since this list goes on forever, this list has to eventually repeat itself. Because if it didn't repeat itself, we'd have infinitely many elements in H, and that would contradict H being finite. So since H is finite, this sequence must eventually repeat itself. So in other words, it has to be the case that some power of A is equal to some other power of A. You say AI to the I equals A to the J for some I in J with I strictly greater than J, strictly greater than 0. So in other words, you have to be able to find two different powers of A that are equal to each other. Because if this didn't happen, then all of these would be distinct elements, and we'd have infinitely many elements in H, which would contradict H being finite. Questions or comments so far? All right, we're ready to identify what I claim A inverse is. I claim that's going to be our A inverse. So let's see if we can prove that. First of all, I'm going to notice that if we take A to the I minus J and we multiply by A to the J, what's that going to give us? Keeping in mind that I minus J is positive integer.
Oh, I was over the
I'll give you a hint. This is not a trick question.
Was it AI?
Yep.
Okay.
Basically saying if we have I minus j copies of A, and we're combining them with j copies of A, we're ultimately going to be left with I copies of j. Well, we assumed that a to the I is equal to a to the j, which is equal to the identity element times a to the j. This is from what we said here, a to the I equals a to the j. A to the j being equal to identity times a to the j, well, not just because the identity element's the identity element. Thus, a to the I minus j times a to the j is equal to the identity element times a to the j. So by cancellation, here we're using one of our theorems from last week. What can we say? We assume that a to the I minus j times a to the j is going to be equal to the identity element times the same a to the j. So if we use kind of this cancellation property that we have for groups, Megan? Bingo. A to the I minus j has to be the identity element. Then, since a to the I minus j is the identity, I claim we could take a times a to the I minus j minus 1, and we'll get the identity element. Because that's just good. When we multiply these out, that's just going to give us a to the I minus j. What does that tell us about A inverse? It has to be this a to the I minus j minus 1, since a to the I minus j minus 1 is something that we can multiply a by that will give us the identity element. If we can multiply a by something and get the identity element, that automatically tells us that something has to be A inverse. So here's the kicker. What do we know about a to the I minus j minus 1? And here we're using the fact that I is strictly greater than j is strictly greater than 0. Right?
It has to be in H.
It has to be one of the elements in this list, all of which we said are in H. Therefore, it has to be in H. Since a to the I minus j minus 1 is one of the elements in our sequence. Gadzooks. All this work to show, given any element A in H, A inverse also has to be an element in H. Because now we're basically done with the body of our proof. Now we can write our conclusion. Out of room to write the conclusion. So we have to erase the introduction. Thus, by the two-step subgroup test, H is a subgroup of G. We assumed that H was a non-empty subset of G with closure. We proved that H then also has to have inverses. Therefore, it's a subgroup. And notice that we had to rely on this finite property. So one last question to think about. Is this theorem still true if H isn't finite? Meaning, if we're given any subset H of the group G, where H has closure, does H, even if H is infinite, does H have to form a subgroup of G?
Not necessarily, because the sequence doesn't complete itself.
this is true, that we can't use this proof in order to show that that has to be the case. That doesn't necessarily mean there's not another proof out there somewhere that also doesn't work. If you want to claim that the answer is not necessarily, I think you have to come up with a specific counterexample of some infinite h which does have closure, but still doesn't form a subgroup.
If G is all the integers under addition, and H is all the integers from 0 up, then you'd be able to add any of them to get another integer within H. But it doesn't have inverses, so it's not a group.
I like it. Yeah. Yeah, that's a great counterexample. If our group is the group of integers, H is the set of all non-negative integers. So this is just an example. Then H has closure. In G, because if you take any two non-negative integers and add them together, you'll get another non-negative integer. But H is not a subgroup because nothing other than 0 has an inverse. Yeah, nicely described. But H is not a subgroup of G since, for example, let's go with my favorite. 27 has no inverse in H. Twenty-seven is my favorite number, by the way. So if you want to show, like, this theorem doesn't necessarily have to hold if we remove this assumption, it doesn't quite work to say, oh, we can't use this part of the proof breaks down. You have to actually be able, because there may be another proof out there that doesn't necessarily rely on finite. You have to actually come up with a counterexample in order to show this property doesn't always hold. And so here, we found an infinite H that has closure, and it turned out that that infinite H didn't have to be a subgroup of G. By the way, less than or equal to with a slash through it is how you say not a subgroup of. Don't say greater than. That has no meaning. And so this shows that in order to be able to just rely on closure to say it's a subgroup, you need to also know that it's finite. So this could be a way you could show subgroups of D3 and D4 are subgroups just by checking closure. Okay, that's going to do it for today. Sorry to keep you a couple minutes over. When we come back on Wednesday, we're going to start talking about a special type of group called cyclic groups and get into chapter 4. Have a good day, everybody.